All right. Hello and welcome, everybody. I am Erin Broberg with Sanford Underground Research Facility, and during tonight's event, we're going to have Dr. Luther Beegle from NASA's Jet Propulsion Laboratory with us. If you sit tight for just a few minutes, we're going to take a moment for everybody to filter into our Zoom webinar and for our stream to go live on Facebook. Oh, wow, we're live on Facebook already. That's terrific. Okay. So if you're just joining us now, you are in the right place. We're going to go ahead and get started. Again, I am Erin Broberg with Sanford Underground Research Facility, and tonight's event is Deep Talks Looking for Life on Mars with SHERLOC. So before we get started, we want to take just a minute to thank all of our amazing Deep Talks sponsors who have sponsored us this entire season with this short video. Awesome. Thank you so much, sponsors. And one of those sponsors, Crow Peak Brewing Company, is sponsoring tonight's door prizes. We're going to have 3 prizes tonight. One is a growler with 1 fill. Another is a 6-pack of Crow Peak's locally brewed craft beer. And then the final one is a gift certificate with a Crow Peak t-shirt. So some fantastic prizes. We've got the poll up right now if you're joining us via Zoom. We're going to give you just about a minute to enter yourself. The poll is only available to Zoom webinar viewers. So if you're watching on Facebook, next season you can join us on Zoom for a chance to win. There are 2 things about this door prize. 1, you must be 21 years of age or older to win. And 2, you must be able to pick up the door prize at Crow Peak Brewing Company in Spearfish, South Dakota. So please make sure if you fit both of those criteria that you enter yourself, and we'll randomly select a winner after the webinar is over, and we'll contact our winners via email. All right, I'm going to give you just a little bit more time to select the option to enter yourself. How are we doing, Matt? All right. Well, if you are just joining us, thanks for joining. Go ahead and enter yourself to win the door prize from Crow Peak if you are 21 years of age or older and can pick up the door prize in Spearfish, South Dakota at Crow Peak Brewing Company. All right, 10 seconds to enter yourself if you haven't yet. Again, thank you so much to Crow Peak Brewing Company and all of our fantastic sponsors. It has been a terrific year, and we're so grateful to everyone who supports us. All right, we're closing it down. Thanks to everybody who entered. Tonight, as always, we would love to hear your questions. So if you're joining us through Zoom, please use the Q&A function to submit your questions. And if you're watching live on Facebook, add your questions to the comments section. I am excited to introduce tonight's speaker, Dr. Luther Beegle, the principal scientist at NASA's Jet Propulsion Laboratory and principal investigator for the SHERLOC instrument, which is currently examining Martian rocks for signs of ancient life. Tonight, he will discuss the ups and downs of looking for life in the universe through robotic exploration. Dr. Luther Beegle, thank you so much for joining us tonight. I'll hand it over to you.
Hi, thank you very much. Thank you very much for having me. I'm going to go ahead and just dive right in so we have plenty of time for questions. Let me, sorry. I got to do this, screen share. All right, hopefully you're seeing my slides in full screen mode. Is that right? I'll take that as a yes. Okay, so I'm Dr. Luther Beegle. I'm going to talk about SHERLOC. That's a picture of me eating ice cream in Greenland. I thought it was a apropos picture because we were in Greenland trying out some of the technologies that went into SHERLOC. Literally a cast of thousands on this. We'll talk more about the acknowledgements at the end. So this is Mars. Mars is the fourth planet from the sun. It is the fascination of many astrobiologists in the solar system. It is the most Earth-like planet in the entire universe that we've found so far. It's a real mystery of what Mars is, of what Mars was, and what Mars could be. It had ample evidence of liquid water right around the time Earth had ample evidence of liquid water, and life started on the Earth. Mars is someplace that I think about all the time. When I was a little kid, I wanted to travel to Mars to look for life, but then I realized A, I don't like to fly, and B, the pandemic is, I've realized in the pandemic that being in a small enclosed space with the same people every day is not necessarily something I'm good at. So instead, I'm glad that I decided to go into the robotic aspects of Martian exploration, and that's where we are today. Mars has been fascinating to astronomers since basically the beginning of time. It was one of the six wanderers that the ancients knew about that moved along the stars. And then once we started building telescopes, we went into this idea of what Mars was. And so we started looking at Mars, and the general consensus was, wow, you know, it looks like it's an Earth-like planet. There's probably life on it. I think back 100, 150 years ago that people would have thought there was life on it. So one of the things that we did when we first got to the space age was we started sending probes to other planets. And one of the first places we went to naturally was Mars. The first probe we sent there was Mariner 9. It flew by the planet, took a bunch of pictures, and did some measurements on the way. And what it found wasn't a planet that was that had any kind of life associated with it at all. It looked like a cold, dead planet that was very dry as it zipped by. However, there was ample evidence through images, like this image you see here, of rivers and other things that made it seem like at one point Mars was wet. So that became a real question of whether Mars could still have life associated with it, whether it did have life, and really where did the water go? And over the years, we've continued to search on it. We have discovered that while modern Mars is cold and dry with polar caps, that in the past it was warmer and wetter, and this is an ancient, this is an artist's rendition of where liquid water would be. We know lots of different places on Mars, and everywhere we go, we look, we see evidence of water and fluvial activities. I give a talk in Death Valley every single year at the Dark Sky Festival. And one of the things I do is I send a lot of pictures that are Mars on one side and Earth on the other, and I kind of mix them up and ask the kids in the audience which one's Mars and which one's the Earth. And so these are some of those slides. And so you can see here that one of these pictures is from the Earth and the other picture is from Mars. The one on the left here is a Martian picture. The one on the right is an Earth picture. But this was obviously, you can't really tell the difference. And when we see this as a geologist, we basically assume that both things were created in the same way. So the picture on the right is a dried stream bed, riverbed in the desert. So we assume that the same processes that form this stuff on the right form the stuff on the left. And we also see from orbit, we see hundreds of other different places that had liquid water associated with them that have an analog on the Earth. The two pictures on the top, A and B, are volcanic activity, where there's some fluvial features in these particular ones. One of them is from the Earth, one of them is from Mars. The ones below is fluvial activity again. one is from the Earth, one is from the Mars. And what this shows is that when you're looking at Mars as a whole, Mars, I don't think any planetary scientist didn't believe there was a lot of liquid water on Mars for an extended period of time. Now, the trick to deciding which one is Earth and which one is Mars really is you look for features that either have life associated with them, like grasses, or you look for something like what you see on the picture on the bottom left, which is a road. There are no roads on Mars, and you can actually see, this is a picture from Death Valley, the canyon in Death Valley, where the road goes around this alluvial fan as it goes out into the desert. The one on the right does not have a road because it's on Mars and there are no Martian roads. So if we were going to go look for life in the solar system, really, what do we look for? The biggest problem right now with looking for life is even defining what life is. There's no real good definition. If you look in the dictionary, underneath life, there's always the word alive in the definition, and that doesn't really work well as the circular argument. It's really hard to define life because we have one known example of life in the universe, and that's on Earth. We kind of know it when we see it, but it's really hard to define. We still have lots of discussions on whether viruses are alive. So from a scientific perspective, we have to ask ourselves, okay, really, what are we looking for when it comes to life? Well, life as we know it needs three major things. One, we know it needs liquid water. All life on Earth requires liquid water to survive. It's the main solute in all living things. We also know that all life on Earth is based around organics and organic material. These are carbon-bearing molecules, amino acids, lipids, proteins, RNA, DNA, things like that. We know life needs organics, and we know life needs an energy source. And that can be many different forms. Right now, when we look out the window, we see green, we see a lot of chlorophyll. This is all photosynthetic life. But there's other places where life uses other energy sources at the bottom of the ocean, at the bottom of a mine, which I'll talk about in a second, where it's using chemical life forms. So really what we look for, and when we go search for life in the solar system, is we want a place that has water or had water, a place that had organics, and a place that had an energy source. Usually that energy source is volcanism in the solar system. So when we talk about other bodies other than Mars, like Europa and Enceladus, we assume there's energy sources because we know they have liquid water, and we're assuming there's hydrothermal vents in the bottom. Additionally, we also know a couple other things. One, we know life has trouble with wide temperature swings. So we don't want to go look for a place that temperature changes a lot over days. And I'll talk about what more ramifications of that in a second. We also know that while life can handle high levels of radiation over an extended period of time, a year, 10 years, 100 years, the high levels of radiation, gamma rays and galactic cosmic rays, things like that, life does not like high levels of radiation. There's a lot of evidence of that. And the last thing is the organic molecules themselves really don't like UV photons. So if you get down below about 300 nanometers, life tends to stop liking things like that. So this allows us to start discussing where we're going to go look for life and how we're going to go look for life and some things we would look for, basically water, organics, and an energy source. So given the fact that Mars was wet, and we knew this back in the 1970s, we talked ourselves into this idea that we're going to go to Mars and we're going to directly look for life. So we made and constructed the Viking missions. There were two missions. They had two orbiters and two landers. They went to Mars. They landed on the surface. It's the first touchdown on the surface in 1976. And what these instruments did was they picked up a little bit of Martian soil and they fed it liquid water and they fed it nutrients. So they gave it some fuel, they gave it some liquid water, and they wanted to see whether or not anything was going to grow out of the material that they provided. What they failed to take into account when they did this was they failed to take into account that there are chemical reactions that sometimes take place when you have a reactive soil. And places that have reactive soils are places that have a lot of UV radiation and are dry. Mars has a lot of UV radiation and is dry. So when the two Viking missions scooped up some material, they had 3 different experiments. They put them in those experiments, and the experiments were vastly contradictory of what they thought was going on. There was a lot of questions about what we actually saw. And it took a fair number of years to determine that it was a chemical reaction that actually took place, that there was no life on the surface, and that there was probably no life at all on the surface of Mars because of those things we know life doesn't like. We started measuring radiation effects. We started measuring the amount of access to liquid water. We measured the organics, and we didn't find any organics. So that was basically it for the better part of 20 years. But in those 20 years since Viking, what we started to figure out is we started figuring out more about life on the Earth. And what happened was we came to the realization that life on the Earth is much, much more different and much more interesting than we ever could have imagined pre-Viking. We went to places where we didn't expect to see any life because it really messed with our idea of what life was. We went to the Antarctica. These are the dry valleys in Antarctica. In this particular valley, it gets above 0 degrees Celsius about 2 weeks every year, and there's very, very little rainfall. It's one of the driest places on Earth. And inside some of the sandstones in this very inhospitable place, we find evidence of bacterial colonies. We take the sandstones, not all sandstones, but some of the sandstones, you break them open, and you see this wonderful bacterial colony just having a wonderful time inside this sandstone. Nobody had really thought that this could be possible in the past, and it really started making us think about what life was. We also did a lot of research in mines, and this is actually one of the active research projects that we had at JPL, trying to build instruments to go look for life. This particular experiments were done at the Sanford Underground Research Facility, and about 5 kilometers underneath the surface, we went down and we picked up water that was coming down from the walls that had no access to the surface, had no real energy sources that were obvious, and we collected samples. Other researchers have done this, and they found life because there was a lot of energy stored up in chemical energy in the material between where the water was flowing. So once again, if you had water, there was organic carbon in the area, and you had an energy source, which is here chemical energy sources, you found life. Nobody ever thought this would be possible back when Viking was going on. So it really did change our idea of where you could find life and what life would look like when you got there. And this is Haley Sapers, a postdoc of ours, actually down at the bottom of the mine collecting samples to come back to the lab to analyze them for which bacteria they're going to find. The other problem we have on the Earth is that there's a very dearth of really, really ancient rocks around the time when life started on the Earth. So we know life started on the Earth around the life on the Earth had started about 3.6, 3.8 billion years ago. There are very few rocks left over from this particular age. So all of the evidence of what the Earth was like 3.6 to 3.8 billion years ago has pretty much been destroyed, except in these very sparse regions across the globe. We've been to Isla in complex in Greenland. We'll talk about it in the next slide, and in Australia, there's some evidence that there's life in these rocks, but really a lot of what we know about the origin of life on the Earth has been lost to geologic time. And a lot of this is because of plate tectonics, geology, and future weathering from different processes on the Earth, including terrestrial life eating the old life and eating evidence of the old life and moving things along. So like I said, you can go back in the ancient rock record and make a determination of whether certain features and certain evidence is of life. So the picture on the right here is a picture from the Australia Pool Formation in Australia. We were there a couple years ago looking at the samples, and what these are called stromatolites. And what makes these look like they were alive is the way the layering works. Different formations have different visual textures and different feels to them. And it looks like something was growing in the middle of these layered deposits. And then you look at the layered deposit, you look at some of these features, and they have isotopic evidence that they were alive at one point. The same thing you can kind of see in a Greenland, in Isla on the left. These aren't as obvious as the ones on the right. So we're still arguing about the ones on the left. So we're not sure if this 3.7 to 3.8 billion year old rock on the left has life associated with it, but we do know the one on the right is pretty much the general scientific consensus is they were formed by little microbes. And I should say the rest of the talk is that most of the time when I talk about life is little microbes, single-celled organisms that dominated the Earth for the first 2.5 to 3 billion years. And we think that if life started on Mars, it would be all in single-celled organisms. So among this discussion of what life is on the Earth and what life could possibly be on Mars, in 1996, a paper came out that analyzed the Allen Hills 84001 meteorite that was picked up in Australia and Antarctica back in 1984. And inside this rock, this group of researchers found evidence that they claim is Martian life. And one of the main pieces of evidence is the SEM image you see here, which looks like a worm-like structure, which would be like a bacteria normally. Now, it turns out that most of the lines of evidence that they had reported in this particular paper, most of the scientific community believes could have been created through abiotic processes, which means it could have just been created through regular, normal, everyday hydrothermal vents, things like that. You don't need life to go to actually create it. And because of that, we no longer think that this is evidence of ancient Martian life. But what it did do is it got a lot of us thinking. This particular rock got a lot of us thinking, which is, how would we find life if it was very sparse on Mars? And this rock had basically started the entire journey of a lot of us to figure out how best to go look for ancient life on Mars, and how we would actually prove it and what we would actually look for and things like that. And so we started thinking about what different types of measurements we would make for life. So there are a lot of different things you'll see in the literature. Elemental abundances, life loves carbon, hydrogen, nitrogen, oxygen, phosphor, and S in different materials. And basically life will concentrate these particular elemental abundances in a sample. So if you were looking at a sample and you saw the schnapps basically concentrated, you could say, well, that could be what is called a potential biosignature. We know life likes to breathe stuff in and breathe stuff out. A lot of life, early life on the Earth used methane, and it breathed in methane, and it used methane as an energy source. You would see a different distribution of these hydrocarbon chains if life was actually breathing them in and breathing them out. Life likes amino acids. Terrestrial life uses approximately 20 amino acids. Abiotic synthesis, when we find amino acids in a meteorite, we find 50 or 100 or 500 or 150 different types of amino acids in meteorites. If we found a meteorite that only had 10, and those 10 were specific, then we might be able to say that's a potential biosignature. We know that life likes fatty acids, specific fatty acids with 16 or 18 carbons in a chain. We know life likes to clump together. Life is very clumpy. If you look at life on the Earth, if you look at the life in the pictures from the sandstone from Antarctica that I showed, life is clumpy. Life was just in that upper centimeter. The rest of the rock has absolutely nothing in it, but life is clumpy in that particular region of the rock, and life should leave behind, as it dies out, different clues, basically larger assemblages of units like nucleic acids. Life also likes different types of isotopic measurements. So one of the things that we can measure is the carbon ratios, and that can tell whether something is alive or something isn't alive. But all of these things, there's nothing really on here that is basically would be a smoking gun, including chirality, because you're never quite sure. You could point to one particular measurement to make that determination of whether there was life in that particular sample. So because of the rock, the Allen Hills 84001, a lot of programs started off to build small instruments and take them out into the Earth, terrestrial environment, to determine whether or not they can actually detect life on the Earth. Because as we all know, there's life everywhere on the Earth. In Arctic dry valleys, there's life in glaciers and the like. And if you can't find life on the Earth, it's really going to be difficult to send something to Mars to look for life here. So we had a research grant. We went to Summit, which is in the middle of Greenland, and we drilled down 105 meters in ice depth. Looked at a borehole. The instrument was attached to the drill. We went down into that drill to determine whether or not we could find life, and we did. One of the things that is really interesting is that for different types of deployment of an instrument, you have to have different types of accommodations associated with it. Our instrument, this is a knockoff, not a knockoff of SHERLOC, but this is a SHERLOC-like instrument that is attached to the drill, and it's going to look completely different than the instrument you're going to see that we sent to Mars. And we basically lowered this instrument on top of the drill. It went down into the hole. We looked out the side to determine whether or not we could identify signs of life. And we did a pretty good job of identifying organic material in that ice, which was a real accomplishment. We also try other different things in our laboratory. So one of the things you'll notice is that it's not just the instrument itself, but it's the payloads and the way you deploy the payloads that really change how you look for life. So if I was going to go to Mars and I was going to look on a cliff, because a cliff face is a pretty good way of looking at stuff that could have been buried, we tried to build this rover called a lemur, and what it is it's a cliff climbing robot. It uses its pads that have little tentacles on it that allows it to capture onto the wall, and it actually climbs up almost a 90-degree wall. So if we were going to go to a place like the moon and look inside a crater, or a cave, you could actually use this to climb inside the cave, examining the cliff wall as you went in. You could send something like this to the Valles Marineris, which had evidence of liquid water flowing into it, and you can look at one of these outflow channels and use your instrument package to look for life there. So Mars exploration, after Viking, Mars exploration took about a 20-year hiatus that we could actually recalibrate everything. And what the Mars exploration and NASA did was very smart. They said, let's go back to first principles. So the first thing we need to do is we need to figure out how to land something on the surface. So let's send a tech demonstration, a little soldier and a rover with a met station. So we want to learn more about the atmosphere of Mars. So we sent the little rover. We learned how to rove across Mars. We went a whole 30 meters, I think, total. We had an instrument on top of the soldier and a rover, and that instrument then determined what the elemental abundance of this rock called Yogi was. The soldier and a rover went up to it, deployed its instrument, and looked at it and determined what was in Yogi. Then we said to ourselves, okay, we know a little bit about how to land on Mars. We know a little bit about how to make instrumentation. We know a little bit about how to make rovers. So let's do the next thing, which is let's go understand Mars geology. Let's go understand the history of Mars. And what better way to do that than to deploy a field geologist? And the picture you see up here is an artist rendition of the Opportunity rover that flew early on in the early 2000s. We went to two different places, Columbia Hills and Gusev Crater, and basically did geology. So we wanted to learn about the history of Mars, and we learned an awful lot at these two individual places. And these rovers roved over the surface, had an instrument payload that looked at just mineralogy. It looked at elemental abundance and the state of iron, and it took microscopic images and did some spectroscopy from the rover and determined that both Gusev and potentially Columbia Hills could have been a habitable environment meaning that there's no reason why life couldn't have existed there when water was there back in the ancient days. So then we went and looked up at the northern latitudes, and we deployed a mission called Phoenix. And what Phoenix did was Phoenix looked for water, because we know in the northern latitudes, Phoenix landed around 70 degrees north, and there was permafrost up there. So Phoenix deployed its robotic arm to actually try to touch some of the ice water that existed on the surface. But what Phoenix did more than anything else is it made a couple measurements that explained why Viking saw what it did. Phoenix had a chemistry experiment on there called Mecha, and another one called Tiga. And what they did was they really understood why you got the results you got on Viking, which was there's a prevalent chemical on the surface called perchlorate. When you heat perchlorate up, it releases oxygen, and it will look like something. It'll look like exactly the results you got out of the Viking experiment. And that was actually really cool, because now we can start building experiments that don't use heat and don't use, that basically don't get a mixed result because of the perchlorate. So from there, we launched the Curiosity rover. The Curiosity rover is the size of a Mini Cooper. It's 900 kilograms. For reference, Sojourner was on the order of, I think it's 25 kilograms. The MER exploration rovers were on the order of 180 kilograms. And now we've got a 900 kilogram, chemistry lab that went across the surface, including a GCMS and an XRD, X-ray diffractometer, to look for mineralogy. And what Curiosity did was it landed in a region called basically it landed at the base of Mount Sharp, it's actually in the process of going up Mount Sharp, and I worked on Curiosity for about 8 years. It is taking material and analyzing it for organic material. It did find some organic material, some really large scale organic molecules that probably aren't associated with life, but are probably associated more with abiotic activity on the surface. But it did find an environment that when this particular, when Gusev Crater was a lake, Gale Crater, get the two mixed up sometimes. When Gale Crater was a lake 3.5 billion years ago, you could go up with a cup, drink the water out of it, and you would have been fine. It was a pretty good habitable environment. And so that was really exciting because it's the first time we showed that the lake water on Mars would have been the same as lake water down the street from anybody else. A nice pH, didn't have anything too bad in it, and was probably drinkable. The last mission we sent up there before Perseverance was the InSight lander. InSight is up there specifically looking at seismometry. It has no life detection instrument, but it has defined what the interior of Mars looks like. So, so the next big thing in Mars would be, after we've identified a habitable environment, after we understand the geology, after we really start piecing together the history of Mars, is to send the next set of missions to actually go look for life. And that's what the Perseverance rover is. Now, I mentioned earlier that it's hard to imagine one particular measurement you could make to say, wow, this was alive, or, you know, there is no life associated with this at all. So what Perseverance is doing is it does have a couple instruments, including SHERLOC, to look for potential biosignatures, which means this really could have been alive, but it also has the ability to bring back samples. So we can bring back we're going to collect samples that are well scientifically characterized. We'll bring them back to Earth. We'll put them in we'll explore them with our labs in the 2030s. And we'll be able to tell a lot more about whether or not there was biosignatures associated with it. So the four objectives of the Perseverance rover is geology. We want to understand, we're going to a new place on Mars. We're in the middle of Jezero Crater. We want to understand the history of that Jezero Crater. We want to do astrobiology. We want to look for potential biosignatures. We want to identify samples. These are going to bring back. We're going to cache them. We're basically going to bring, I think it's 10 centimeters now, 1 centimeter in diameter, basically rock cores. We seal them up and we bring them back in the 2030s. And we also want to prepare for humans, because we're always preparing for the next generation. So the geology, this is what we look for in geology. We want to look for a lot of things over different scales. This rover has 23, our Perseverance rover has 23 different cameras associated with it. So we can see stuff as big as a mountain, and we can see stuff smaller than a human hair. They want to look for astrobiology. This is the Curiosity place I told you about that was habitable. This is Yellowknife Bay. We want to find a real good area in Jezero Crater that reminds us of what Yellowknife Bay was. And we want to collect the samples and bring them back to Earth. We can bring up to 30 samples back to Earth, and we have the ability to actually capture 40 of them, so we can actually pick and choose which samples we're going to bring back and which ones we're not going to bring back. So as I said, the rover has 7 instruments associated with it. SHERLOC is in the upper right-hand corner. It's got a camera called Watson. We'll talk a little bit more about that and the wonders of acronyms in a second. Pixel is an elemental abundance spectrometer. It does X-ray spectroscopy, and it can tell what the elemental abundance is on a 100 micron scale. We have a meta weather station. It tells us humidity, temperature, pressure, wind direction, things like that. Mastcam-Z takes wonderful images. Some of the panorama you've seen comes from Mastcam-Z. SuperCam is a LIBS, laser-induced breakdown spectrometer with Raman spectroscopy and IR spectroscopy. So it looks at what elemental abundances are there, some mineralogy, and takes really good pictures. RIMFAX is a new instrument that has never been flown before. It is a ground-penetrating radar. It can tell us layering down to about 30 to 40 meters underneath the surface. And the last instrument is one of those instruments that are preparing for humans. It's called MOXIE. It ran a couple nights ago, and it produced actually oxygen out of the Martian atmosphere. And what that oxygen is for astronauts to breathe, plus it enables us to have rocket fuel on the surface of Mars to create rocket fuel for humans to actually come back so they don't have to bring the oxygen with them. This is Jezero Crater. It is obviously a river delta. You can see it from orbit. It looks like a river delta. It has all the evidence of being a river delta. It's got the mineralogy of what a river delta would be. River deltas are great places to go look for evidence of life, especially ancient river deltas that are clear, because they are very good biosignature preservation. As material comes in from above, you get more samples that come in on top of each other. They make layers, and those layers protect the really fragile organic molecules and other features on top of it from being destroyed by UV radiation and galactic cosmic radiation. Plus, biology really can change the way the river delta looks. So you could see textures, and you could see forms that are different if there's life versus if there's no life and it's just gravity working for you. This is a picture of Alaska runoff from NOAA. So this is what Jezero looked like most likely 3 billion years ago. It had a river coming in from the above, and it had a river coming out below, which means there's a lot of change in what that lake would look like. And change meaning chemical energy, meaning there's a place that life could actually eat something, which is another reason why we like Jezero Crater as a potential place that life would have existed in. So we launched in 2020. COVID hit 6 months before we got to the launch pad. For those of you who understand the way the planets move, you can only launch to Mars every 26 months. So when COVID hit, we were really worried that we weren't going to be able to get to the launch pad. This was February. We launched in July. It's a Herculean effort by a lot of people to make sure we got to the launch pad. Otherwise, we would have had to wait 26 months to launch again for the planets to come back in orbit around each other. And this is pretty much why. Sometimes Earth is on the other side of the sun. Sometimes Mars is on the sun. They really do have to be co-located to be able to get there in a reasonable amount of time. We landed on Mars. We used the sky crane maneuver. The sky crane maneuver, the cruise phase comes in the upper left-hand corner of this image. It hits the atmosphere. You lose a lot of energy. The heat shield heats up, but at a certain point, that heat shield no longer works. And this is actually an image from the rover itself watching this parachute deploy. So we dump a lot of energy. We're traveling 17,000 miles an hour when we hit the upper atmosphere, and we've got to get to 0 miles an hour in 7 minutes, which is why they call it the 7 minutes of terror. So we hit the upper atmosphere, the cruise stage deploys, the heat shield takes up a lot of energy, and then we get to a point where the heat shield is no longer working. We deploy a parachute, and you can see the parachute get deployed here, and then all of a sudden the parachute's deployed, and we sit on the parachute for a couple more minutes. The heat shield then deploys. This is actually a picture of the heat shield from the bottom of the rover looking down. The rover is inside the back shell at this point, and this is a picture of that heat shield actually breaking away. Then what happens is the rover then starts to get the ground, and this is a picture of us looking up, and this is a picture of the rover itself as we're trying to determine where the ground is. At a certain point above the ground, the parachute no longer slows us down anymore, and we've got to do something else, which is where the retro rockets come in. The retro rockets, the radar finds where the ground is. We deploy from the back shell. The sky crane lowers us to the surface. It fires its retro rockets, and here it's actually firing retro rockets that you just can't see it because it's hydrazine. And the sky crane hovers above the rover as the rover hits down on its feet, and then the sky crane flies off. And this is a picture of actually from the sky crane of the rover getting ready to hit the ground. There's some really great videos of it online. They don't tend to work very well on my computer. I highly suggest looking at them from YouTube. You can see it from every different angle. And then what happens is the best part is that the rover has to, the sky crane has to fly away. Now, at this point, most people saw this and said, wow, this is really cool. But I saw this sitting here in Pasadena when these pictures came down, and I saw all these rocks. Every little dot of black on this particular thing is a projectile that could be hitting my instrument and could be destroying my instrument, because we did not really know how many of these things were going to be flying so fast, and we didn't design the instrument to do that. So we looked at this and we freaked out for like 3 or 4 days until we turned the instrument on to make sure it was working correctly, because a rock traveling at a large rate of speed in a small instrument could actually do a significant amount of damage. Thank goodness it didn't do any damage. This is one of my favorite pictures ever. This is a picture from MRO of the actual, you can see the parachute here on the top, and then the heated, the rover here underneath the parachute against the backdrop of Jezero Crater. So this is where we landed. It took 2 days to figure it out. This is a 15-kilometer landing ellipse. We knew we were going to land somewhere in there. We had terrain relative navigation, so the rover itself could move itself around to make sure that it didn't land on anything hazardous. And then we landed and everything was good. So this is the Mars 2020 rover as they show it on, as you'll see it shown on different websites and things like that. I am not bitter at all because SHERLOC is actually in the backhand corner, and nobody puts baby in the backhand corner. So this is the way I would rather them show the rover itself, so that SHERLOC is out front and then everything else on the rover is in the back. And this is the SHERLOC instrument. So challenges of developing a UV instrument on a robotic arm. So we're sitting on a robotic arm on Mars. The first thing is that you have to develop an optical system. For those of you who have cameras, or I know the weather changes a lot in South Dakota, and the temperature gets really hot and really cold. On Mars, it gets really hot and really cold every single day. We have to be able to survive temperatures from a -128 in cruise to plus 70 degrees C on the Earth. And it has to operate anywhere between -80 C and plus 50 C. If you've ever been into a place that gets that cold, and I'm sure most of you have, you realize that there's a lot of things that don't really like to work at -80 C, and you got to keep them warm up. All of our stuff has to be operable and survive these particular temperatures. SHERLOC itself is basically the size of a shoebox, and there's 26 optics in there, and they all have to be aligned to within a couple microns in order for the instrument to work. And that was very difficult to do with temperature swings of that happen every single solitary day. There are things inside SHERLOC that want to be hot, and there are things inside that want to be cold. They've got to be hot and cold at the same time. That's very difficult to do in a tiny little box. That itself took years to do. We have 3 CCD detectors that are integrated into one spectrometer with 2 imagers, with 2 different actuators. All need to be smart enough to put in cruise and shaped to be accessible to actually get to the surface. We're on the end of a robotic arm, and that robotic arm does not know sometimes where the surface is, and we've got to be able to be deployed without running into the surface. And that robotic arm is on the order of 70 kilograms, and the robotic arm places us to within 5 centimeters of the surface. And all of that has to happen robotically. We operate from a 1.5 meter, 90 kilogram total, including the arm, and we have to get within a few millimeters of where we need to be above the surface to be able to scan and identify 100 micron features on the surface. That's itself is very difficult. For those of you who are high voltage aficionados, we have to use high voltage in a very low pressure environment. And what that can be called is it's very difficult to do because like electricity at 100 volts, 1,000 volts wants to zap things. And if we see any zaps, we reset the rover, and that would be bad. We also have to worry about, account for contamination from outgassing of the rover. UV does not like or loves organic molecules, but it also dislikes other things. And we didn't want anything from the rover to contaminate us as we're going down. That is, we didn't want to identify things we brought with us as a potential biosignature. If I saw a fingerprint of somebody on the surface of Mars, it would be bad because, on a piece of equipment, because those molecules could get on the surface. So all of those things happen, and the biggest problem with building a spectrometer to go to Mars is the natural enemy of the spectrometer is the drill, and especially a rotary percussive drill. And we have attached ourselves to a rotary percussive drill. This rotary percussive drill drills into a rock. It's a hammer drill, so it pounds and it rotates, and we had to develop these basically spacers, the vibrational isolators, to make sure that the drill isn't shaking us apart. Anybody who's ever done spectroscopy in a lab knows that if you have a drill in a lab and you're trying to run the spectrometer at the same time the drill is even running in the lab, that's difficult. That took a long time to figure out. So what exactly is SHERLOC? SHERLOC stands for Scabbing Habitable Environments, Phenomena, Luminescence for Organics and Chemicals. It's a fancy way of saying we take really microscopic pictures. We have 10 microns per pixel resolution. We can see human hair. We can see things on scales of about 30 microns and below. We look for potential biosignatures through Raman and fluorescence spectroscopy. We look for aliphatics and aromatics. These things have different roles in life. And we also look for chemicals such as perchlorate. We were asked early on in the investigation if we could do infinity imaging, and we said, no, we can't. But we did decide we could actually add something else on to SHERLOC, and we called that Watson. And they said, well, what does Watson stand for? And we came up with the acronym right away, and we wanted to call it Weird Appendage Tap to SHERLOC for Operations and Navigation. It turns out nobody liked that, so then we changed Watson to Wide Angle Topographic Sensor for Operations and Engineering. So the answer is yes, we do sometimes do the acronym before we figure out what the acronym stands for. And what we can do with Watson is we take rover selfies, which I'll show you in a second, and we can do close-up imaging, and we can take pictures of what's going on in the rover to make sure wheel wear and other things are working really well. One of the things that we do on SHERLOC, because we do spectroscopy, is we can take a picture of a rock. This is a deep sea carbonate that was cleaned, and we were going to do some analysis on it. And we did analysis with SHERLOC. We took the picture of it, and then we zoomed across the surface. And what we were looking for is where organics are. And here in this rock, the dark blue stuff is where there's a lot of organic material after we had cleaned it. We assumed there would be a lot of blue on the outer regions of the rock. We saw that. We saw blue in the fissures. We saw that. What we didn't notice and we didn't understand at first is what this feature was and what this feature was, because it didn't make any sense, because you can't see anything on the rock. It doesn't make any sense that there would be any biology in there, but these were biologic figures. It turns out after 2 weeks of trying to figure out what it was, somebody said, well, that really does look like a fingerprint. And it turns out it is a fingerprint. So what happened was the postdoc picked up the rock, didn't use gloves, wasn't protective, and didn't do good contamination. But it shows that we can actually do fingerprint analysis on a rock with little or no sample prep. And it shows you pretty much how sensitive we are to different organic materials. So one of the other things we do is we take these images of the surface. And what Watson does is Watson will take an image and then we move the arm a little closer to the surface. This was an image of a sample called TD that was taken from about 1.5 meters above the surface. And then what we did was we basically moved the robotic arm in and got closer and closer and closer until we were 3 centimeters above the rock. And what we would end up doing if this was what we're actually doing on Mars today is we're going to go through and look at this particular patch here that has had the dust removed from it, and we're going to do spectroscopy on that particular image right there. And hopefully we'll get those results back tomorrow and they'll look really cool. We also do selfies. This is a picture of the rover with the helicopter in the distance. This was done with the Watson camera. The robotic arm moves. There's a really great video online of watching the robotic arm move through all of its maturations to get this particular image. This was pieced together of 62 individual frames. Now, what's really cool about all of the images on the rover from all 23 different cameras is that all of the images immediately get released to the public on the website down here below, mars.nasa.gov/Mars 2020 multimeter wall images. As soon as we get them back on Earth, they immediately go to the website. You can actually see them, and you can see all 62 pictures here and how they actually went together. And if you are a photo enthusiast, you can actually put this together in your spare time. In fact, when we took this picture, there was the mosaic actually hit those streets before we had finished making the mosaic ourselves, because we had to color balance and do some other things. We have a science team. I'm not going to talk too much about it, but we do astrobiology, Raman spectroscopy, meteoritics, and geology, mineralogy. We have a great engineering team who built the instrument. It's been spectacular. It's worked. I have thousands and thousands of people. These are just a few of them that helped us build everything. With that, I think I'm ready to take any questions you might have. I'll leave you with the picture of the rover selfie, which was basically 20 years in the making. SHERLOC started right after the Allen Hills 84001 paper came out, and we actually landed and started taking images just a mere 23 years after that particular thing came on. So Erin, I'll leave it. I'm done and ready for questions.
Yeah, terrific. Well, that was an amazing talk, and we have lots of people asking questions. So are you ready?
Yes.
Okay. All right. So this is something that you touched on briefly, but I would love to hear a little bit more about it. So I'm going to go ahead and ask the question. How likely is it that some of the landers and rovers sent from Earth have accidentally carried some microbial life, and those living entities are now growing locally on Mars?
It's hard to imagine anything living in that environment, which is why we don't look for extant life. Now, there is planetary protection. We try to clean the rovers as best we can. And we try to get rid of all of the organic material and all of the organisms on there. But it's really hard to imagine. There's very little water. There's a lot of UV, and there's a lot of radiation on the surface. So we might have contaminated the planet. We don't know. But we do take a lot of care in making sure that doesn't happen.
Right. So that leads into another question. You talk about how uninhabitable it is currently. What caused Mars to become so uninhabitable?
So we know it had a lot of liquid water. And what happened was that right around the time that the magnetic field turned off, that water started going away. And what we think happened was the magnetic field turned off, the solar wind started hitting the atmosphere, and it dissociates H2O. And so the H goes out into space, and the OH then eventually goes off out into space, and the O stays around. This happened probably roughly 3.5 to 3.6 billion years ago. And so all of that water gets lost into space. Eventually, the Earth's iron core will stop spinning, and billion years in the future. And when that happens, the magnetic field gets turned off, and the same thing should happen here.
All right. Yeah, speaking of the poles and magnetic fields, We got a question from Facebook that said, are we planning to go to the poles of Mars anytime soon because of the underground lakes?
So there is a potential in that underground lake. There's 2 instruments in orbit. One of them saw it, one of them didn't. They're still debating on whether or not that lake actually exists. So science, as you probably all have watched during, the events in the past year and a half, sometimes scientists like to argue a lot. We're very good at arguing. There is no plans to go to the poles yet, but the way the Mars exploration works is that next mission is going to be Mars sample return. There's 3 launches that have to do that. They're going to go pick up the samples and then basically return them to Earth. We have 3 launches on the Earth and 1 launch on Mars. And then after that, the Mars program is completely open, and you could propose a mission in Discovery or New Frontiers to go to the polar caps and look for anything else. I particularly want to drill. I want to make a mine just like y'all have. I want to go far down underneath the surface, because if there's anything alive today, it is basically underneath the surface, protected from the cold temperatures, protected from the radiation. And we're pretty sure there is liquid water somewhere underneath the surface. It'd be nice to get to that liquid water. And that's the mission I would like to fly, but other people want to fly to the poles, and we'll just have debates over the next 20 years on who gets to choose their mission.
Yeah, that leads into yet another question. Is there an instrument you wish was included in the Mars 2020 mission that wasn't? And maybe it's something that would allow you to go much, much deeper.
I would have liked to have a much larger drill. So there's a limit on the number of the total mass we could actually launch with us, and that's pretty much why we have the payload we have. I would love to do a deep drill on Mars, the 2 to 10 meters, to get underneath the surface. Because, like I said, if there's something alive, it might be underneath the surface. That might not be far enough down to actually find anything extant, but it'd be really fascinating to find out.
Right. Speaking of future missions, are there possibilities of future Mars missions with other countries or with private companies?
So Mars sample return is being done. The Europeans are helping out. I think the Japanese are helping out, and different NASA centers are all helping out. So yeah, we're one of the orbiters that we get our data from is the Trace Gas Orbiter, which is a European mission. We donated some hardware to them, and we help them with their data connection. So we do work really well with the Europeans, and we work really well with the Japanese. Both Hayabusa and OSIRIS-REx, the sample returns from asteroids, are worked with the Japanese. So yeah, we'll do more missions with them, and Mars sample return needs an international component to actually be affordable.
Awesome. And this question is, how different is the process for landing on Mars compared to landing on the moon?
So the moon has no atmosphere, and it's very much closer to Earth. So on the moon, you go around the moon. You basically use rockets to get to the surface, and that's fine. You're not traveling anywhere close to 17,000 miles an hour as you do on Mars. And the reason is that Mars is about 150 million miles away. The faster you go, the sooner you get there, but then the more energy you have to dump when you land. So Mars has just enough of an atmosphere to be annoying, but you can dump a lot of the energy, but you can't dump it all. So which is why you have to go with the heat shield, the parachute, and then the retro rockets. MER was heat shield, retro rockets, and airbags. They had big airbags that bounced the instrument across the surface, but you can only do that with so much mass. So they went a different way, and I don't know how the humans are going to do it, because the humans have to launch 100 tons more than we launch.
Right. And
we call them the humans. We do call them the humans, by the way, in the robotic place. It's the robotics and the humans.
Well, I think that leads into, when do you think people will go to Mars?
As soon as we have the political will to send them there. It's pretty easy to send people one way. You can go there and you can send them there. We could do it soon, and you could basically send food every 26 months and keep them alive basically for the rest of their lives. The problem is bringing them back from Mars, which is the really expensive thing. And so that takes a lot of money. And so if we're going to go colonize Mars, we could do it sooner rather than later. If we're going to want to bring the astronauts back to Earth, then that's going to take a lot more time, because you have to they have to stay on the surface for, like, I think it's 500 Martian days, which are called sols. And then you have to build a rocket to bring them back to Earth, which is a pretty big, expensive endeavor. So I'm guessing if we really wanted to do it and we really put our minds to it now, we could land on Mars before 2040.
In addition to underground at SURF, was SHERLOC technology tested at locations on Earth with the Earth's oldest rocks, like on that map that you showed early on in your presentation?
I have some of those rocks that we look at, and we can tell the textures in them. We've taken it to Greenland, we've taken it to the Mojave many times, and we've taken it to the bottom of the mine. It's also been at the bottom of the ocean. It was on a deep sea vessel, part of the technology. So it's gone down, I want to say it's 2 kilometers under the ocean in the North Atlantic.
Mm-hmm.
And each one of those things is it's a completely different instrument, because you have to rebuild it for every deployment and everything. So it takes a lot of time and energy to do things like that. But again, sorry.
Right. Yeah. No, that's great. Another question asks, would you be surprised if we didn't find life on Mars?
So the fascinating thing, and we talk about this all the time, and I could talk an hour and a half about this question in and of itself. Mars is fascinating, whether it had life or whether it didn't have life. And I'm not going to talk for an hour and a half. If it had life, what that means is that life is probably easy. That whenever you have liquid water for an extended period of time, energy source, and organic molecules, life starts, which is really fascinating. And Mars has really ancient rocks, so we can be able to piece that together much better than we'll ever be able to do on the Earth. If Mars didn't have life, what that means is that life could be really rare in this whole universe. And if life is really rare in the whole universe, you ask yourself, how special are we? Is there a lot of life out there? Is there not a lot of life out there? Both things are equally fascinating to me. And I would not be surprised by either one of those answers.
All right. So this question says, how does the desire to find life on astrobodies influence the scientific method, and how do you avoid bias?
You don't avoid bias because you have to make assumptions. I wouldn't call it bias. I would call it, you need to make sure you're making the right assumptions going into it. And we try not to, we ask ourselves all the time, are we just looking for life as we know it? And we try not to do that. It's very difficult to do because we don't have a second genesis. The first time we see life somewhere else, and we can start really understanding what life is and what life isn't, it'll help us develop these instruments a lot better. But we try not to say, okay, I need to go look for this particular type of bacteria, this particular type of protein, or anything else like that. We just want to go look for large scale organics and then try to piece together what we're actually seeing. And it's really difficult because you get it in your mind. You have to make assumptions going in, like Viking did, but those assumptions sometimes can be wrong. And then you have to make sure that you're getting some data out of your experiment, regardless of if that.
Awesome. Well, we are going over time a little bit. I want to try to hit 2 or 3 more questions because we have so many. I realize we're having a bit of camera trouble, so if I get on and off the screen, don't worry about it. So this question says, how different is the geology on Mars compared to Earth?
There's a lot of similarities. The differences are in chemistry because of the dryness, but there's a lot of similarities. We see mountains, we see riverbeds, we see lakes. The Valles Marineris is a canyon. We see ancient dry tundra. We see places where there was a lot of impact craters in the south. So we tend to land in the north where we have seen this potential ocean, In the south, there's a lot of craters. There's a lot, what you see on Mars more than the Earth is these impact craters, because there's not a lot of weathering to make the impact craters go away. So a lot of the impact craters on Earth get, degraded over a million years or so. But on Mars, if you have an impact crater, it can stay there for a billion years or so.
Right. This one says, how did the bioresearch work at SURF assist the development of the instruments?
So what it did was it enabled us to go in and identify biosignatures in a place that didn't have a lot of biology. The problem with the SHERLOC instrument is we're very sensitive. And so we see when we actually could put a rock down in the lab, walk away, go to lunch, come back, and then there will be organic molecules that are collected on that rock, unless we use a very, very, unless we go into a lot of methods to make sure that the room is clean and put it in the clean room, which then costs a lot of money. But so we see organics everywhere. In the bottom of the mine, the amount of organics in that water was very little. And so it enabled us to test out hypotheses of what life is like in a very, very life poor environment. There's still life there, but there's not a lot of it. And that is a really, interesting thing, because while you can make up those samples, they're not really the complex samples you find in the field. We always get surprised when we look at a different sample from the field. When we went to Greenland, we weren't sure we were going to see biology, and we did. We saw biology, and it was all clumpy. I talked about life being clumpy. In the Greenland ice sheet, all of those organisms tend to cluster around other organisms. So you'll see regions where there's nothing, and then you'll see a clump. And the same thing you see in the bottom of the mine, which is life. There's not a lot of it, but when you see it, it's there, and it's clumpy in that water. But we're still analyzing some of that data.
Right. Okay, so we have some viewers who are thinking very deeply about some of the information. So we'll see if you can answer this one. If the magnetic field turned off and water dispersed into space around 3.6 billion years ago on Mars, and life on Earth began around 3.6 billion years ago, does that mean that life on Earth could have originated on Mars?
So that's panspermia, and there's a whole litany of discussions online, life could have started on Mars and come to the Earth. Life could have started on Earth and gone to Mars. There's a lot of, we know there's Martian meteorites on the Earth. We find them all the time in Antarctica. The Allen Hills 84001 is one of them. We actually, on our calibration target, we have a piece of Martian meteorite that we sent back to Mars because it helps us understand how the instrument's working. So we found this meteorite in the Oman Desert and put it on the spacecraft and send it back to Mars, and we look at it to make sure the instrument's working correctly. But yeah, there's no reason why that didn't happen, as long as the transfer and orbits is a relatively short time frame. I think it's 10,000 years, and spores can actually exist that far. So one of the problems, if you found life on Mars, is how do you know, A, we didn't bring it with us, or B, it wasn't part of panspermia? And what you're hoping for is life that's so different that it basically is completely different. But that's a question for somebody who actually finds life on Mars, and after they're happy for a couple of years of finding life, then they'll get into that, answering the rest of those questions.
Awesome. Love that you had an answer for that. That's terrific. Great.
Yeah.
Well, thank you for sticking around for some extra time to get to some of these questions. We still have a lot more, so maybe we can find a way to address some of them later. But I did want to show you the gift that we got you to thank you for being here tonight. But you're just gonna have to wait. Oh wait, maybe I can start my own video here. All right. Well, maybe people can see me from my different screen now. Awesome. Okay. So I do get to show you the video or the gift that we're going to give you. And it is a photo of the Ross head frame overlooking Kirk Canyon. And
That's cool.
That is what you would see if you were on site looking out the room where we are right now, except it was really rainy and foggy, so you might not have seen it anyway, and that's a better picture. So thank you so much for joining us tonight and giving us an amazing insight into what's currently going on and is very relevant to current research happening on Mars right now. We want to do
Thank
another.
you.
Yeah.
Well, thank you very much for having me, and thanks for everybody for listening. We love talking about this stuff. We could talk about it forever. Everybody on the mission is super excited, and we love getting feedback because it's just a lot of fun, and it's a lot of work, but it's a lot of fun too. So thank you very much for inviting me.
Yeah, of course. We're happy to have you. To end, I just want to say thanks again to our Deep Talk sponsors and the Sanford Lab Communications team that made this event possible. A recording of this talk will be shared on Facebook, Vimeo, and YouTube channels. So please be sure to share that with a friend who may have missed the live event. When you leave the Zoom webinar, you'll be asked to take a survey about your Deep Talks experience, and we would love to hear what you have to say. So please do leave us some feedback on that survey. This is our final Deep Talks of the season. So my reminder for you tonight is to join us for Neutrino Day Star Chronicles, our largest virtual event of the year, on Friday, July 9th and Saturday, July 10th. Thank you so much for joining us tonight, and thank you, Luther, for being here.
Thank you.